Okay, so in the last video we talked about the HR diagram and the different parts of the HR diagram. In this video we're going to start off by talking about what's called the mass-luminosity relation. Now this is not an equation per se, it's just a relationship. We've talked about before how more massive stars have a bigger luminosity, and the reason for that is because the more massive a star is, the more inward gravitational pressure there is. And in order for a star to be stable, there has to be a balance between the inward gravitational pressure from gravity and the outward radiation pressure. And so that means if a star has more mass and has more gravitational pressure acting inward, it also has to have more radiation pressure going outward. In other words, it's going to have to burn hotter and brighter to produce enough heat to balance out gravity. Okay, and so typically more massive stars have a higher luminosity. Now, when dealing with main sequence stars, we have a relationship which is not the same as an equation, but we have a relationship that we can use to solve problems. The relationship that we're going to use, at least for this class, only applies for main sequence stars. And that relationship says that the luminosity of a star is proportional to the mass of the star raised to the 3.5 power. Okay, now for different types of stars, this exponent may be different, but for main sequence stars, the value we're going to use is 3.5. You're never going to see problems with stars that are not main sequence stars. Okay, and so this basically tells us how the luminosity of a star is related to its mass. Now, it's very typical in most problems to be asked questions where you want to know the mass or luminosity in terms of the sun's, our sun's luminosity or mass. Okay, and so if I take this relationship and I, let's say, divide by the luminosity of our sun, which remember the luminosity of our sun, use a L with a circle and a dot, then this relationship, this ratio has to hold if I put the mass of our sun over here also to the 3.5 power. Okay, and so because I know mass and luminosity are related in this way, I can basically come up with an equation, an actual equation, that lets us express the luminosity of any star and the mass of any star relative to the mass and luminosity of our sun. So in this equation where they say L0 or M0, you can think of that as like a reference luminosity or reference mass, and we're going to use our sun's luminosity and mass as that reference. Okay, so in other words, we can use this relationship to express the luminosity of another star in terms of our sun. And so we're going to do a few problems to see how this relationship works. As long as you know what the relation is, these problems just require a little bit of math, but they shouldn't be too difficult. Okay, so pause it here if you need to add that to your notes. I'm going to erase this. And let's take a look at a simple problem. Okay, so this problem says a star is found to have a mass of 10 times that of our sun. Estimate the luminosity of this star relative to our sun. Okay, anytime you see something relative to, that means in terms of. So, and I gave you a hint. It says your answer should be in terms of solar luminosity. Solar meaning our sun. Okay, in other words, the answer to this question, okay, it says estimate the luminosity. It's not asking for the actual luminosity. It's asking for the luminosity relative to our sun. Okay, so our answer should look something like, just to give you an example, it should look something like L equals some number times the luminosity of our sun. Okay, that's what it means when it says like relative to our sun's luminosity. Okay, so the information we're given is that this star has a mass 10 times that of our sun. Okay, so this is a given. The mass of the star, M, is 10 times the mass of our sun. Okay, and we want to use the mass-luminosity relation, okay, which is this, to figure out what goes here in the blank. Okay, so 10 times the mass does not mean 10 times the luminosity. All right, so this relationship has to hold for the star. This relationship also has to hold for our sun. And so if I just divide these two together, okay, then I get the equation that I had written down before that looks like this. Okay, so this ratio, by dividing by this, it turns from a relationship into an actual equation. And so I actually know what this ratio is because it's given in the problem. The ratio of the mass of the star to the mass of our sun is 10. Okay, and so that means that the ratio of L over L sun is equal to 10. Okay, that's just this inside the brackets part, raised to the power 3.5. Okay, and so that means L should be equal to 10 to the power 3.5 times L sun. And so this number right here is the answer to my question. Okay, so I go to my calculator, I put in 10 raised to the power 3.5, which is kind of an awkward exponent to use, but that's what it is. And I am just going to round that 3162. Okay, I'm not going to bother putting the decimal just because all of these things are not that precise measurements to begin with. Okay, and so that's a sufficient answer for this question. So this star that has 10 times more mass than our sun actually has a luminosity over 3,000 times more than our sun. Okay, and now again, remember this relationship, this exponent of 3.5 only holds for main sequence stars. Okay, so pause there if you need to take a look over that, but this would be the answer to the question. Okay, just to go back, okay. Do that. Okay, just to go back for a second, this would be the answer to the question. The question originally asked, estimate the luminosity of the star relative to our sun. Okay, so we've answered the question. Okay, we've found the luminosity, not the actual luminosity, just the luminosity relative to our sun. Okay, so keeping in mind that this number is not actually luminosity, it's not measured in watts, but if we knew the luminosity of our sun, which is typically a given, then we could just multiply to find the actual luminosity of the star. Okay, so I'm going to erase this, and I'm going to do one or two more examples. Example 2. It says a star is observed to have 10,000 times more, is observed to be 10,000 times more luminous than our sun. Estimate the mass of the star in terms of solar masses. So in other words, our goal is to find, okay, the mass of the star is equal to blank solar masses. And we're given that the luminosity is, I'm just going to write this in scientific notation just to make it easier, 10 to the power 4, okay, so 10,000 is 10 to the power 4 times more luminous than our sun. Okay, so if you think about that for a second, you should be able to convince yourself that this is basically the same type of problem we had before, just kind of in reverse. Okay, so now instead of being given, the ratio of masses, we're given the ratio of luminosities. Okay, so I write down my two relations. I divide these two to get my equation. Okay, just like so. And now the only difference is now I have the left side, but I don't have the right side. And in fact, I want to find that part inside the brackets. Okay, so I need to do a little bit of math. Now I know that the left side is equal to 10 to the power 4 because the star is given in the problem is 10,000 times more luminous than that of our sun. Okay, so this ratio on the left side is actually 10,000. And I'm just going to write 10 to the power 4 is equal to m over m sun raised to the power 3.5. And now you have to ask yourself, okay, how do I solve for something that's being raised to a power? Okay, if something was raised to the power 2, that's basically being squared, how do you undo a square? Well, you do a square root. And so in order to solve for this part inside the brackets, I need to raise everything to a power that's going to get rid of that 3.5. Okay, so if it was a square, I would raise it to the power 1/2. Okay, something raised to the power 1/2 is a square root. I'm actually going to do the 3.5 root, that is, to raise it to the power 1 over 3.5. Okay, and when I do that, remember something raised, an exponent raised to a power, basically you end up multiplying those exponents, and 3.5 times 1 over 3.5 is just going to cancel out and give me 1. Now, if I do that on the right side, I also have to do it equally on the left side. Okay, and so this left side over here, I'm going to raise to the power 1 over 3.5, like so. And on the right side, when I do that operation, I just end up with m over m sun, which is what I'm solving for. And on the right side in my calculator, I'm going to do 10,000. Okay, so I'm just going to type that in, 10,000 raised to the power 1 divided by 3.5. Okay, so that is the 3.5 root. And I get an answer that is approximately 13.9. And so my answer up here is 13.9. So in other words, this star that we're observing that's 10,000 times more luminous than our sun actually has a mass that's about 14 times that of our sun. Okay, and so that's how you solve problems with a mass-luminosity relationship. Okay, so again, pause it here if you need to. Okay, so I'm just going to clear this. Okay, and so that's how problems work with the mass-luminosity relationship. And I would do one more problem, but I might save that for another video. Actually, just for fun, I'll put this question up just so you can look at it and see if you can't answer it on your own. Okay, so the example question, it says the Hertzsprung-Russell diagram shows a sun, a star A, and the main sequence. Keeping in mind this relationship, this mass-luminosity relation that we've been using only applies for main sequence stars. It says, using the mass-luminosity relation, determine the ratio of the mass of star A to the mass of the sun. Okay, so remember a ratio is a fraction. So our answer to the question should be a fraction. The mass of star A divided by the mass of the sun is equal to some number. Okay, so use the HR diagram and the mass-luminosity relation and see, pause it here and see if you can answer this question. Okay, so the answer to this question that you should have gotten is approximately 3.7, which rounds up to 4. Okay, this is what the mark scheme looked like for that question. You get 1 point for setting up the ratio relationship correctly, and then 1 point for solving. Okay, you should have done 100 to the power 1 over 3.5, which is 3.7. The 100 comes from the HR diagram. Remember, this left side is showing you the luminosity of the stars relative to our sun. So star A has a luminosity 100 times that of our sun. Okay, so that is solving problems with the mass-luminosity relationship. This slide is basically just showing you that, the more massive a star is, the shorter its lifetime, and we've talked about that before. So the last thing we're going to talk about in this video is what's called Cepheid variables. Okay, so Cepheid variables, I'm going to play this clip for just a second so you can see. Okay, so this is kind of what a Cepheid variable looks like, and you don't need to know why a Cepheid variable works the way it does. It's a little complex. But basically, a Cepheid variable, variable means changing. And so a Cepheid variable is a star whose luminosity varies or changes over time. Okay, something like this. It gets brighter and dimmer over time. And, through observations over many years, we've basically discovered that Cepheid variables have a set period between, when they are brightest and when they're brightest again. Okay, So these are stars that they're getting basically fluctuating in size, fluctuating in luminosity. They get bigger, smaller, with some set period. Okay. Now, it also turns out that the period that they change their luminosity in can actually be used to measure the distance to the star. Okay. Now, the reason we like these Cepheid variables, and again, I'll just show you really quickly. This is a simulation of what they might look like to us, kind of like flickering stars getting brighter and dimmer over the course of several days or weeks. The reason we like these Cepheid variables is because there is a relationship between their period, which we can very easily measure the period, and their luminosity. Okay, and we'll talk about that relationship momentarily. Here's just another animation showing you what these might look like. Okay, now a Cepheid variable is what's known as a standard candle. Okay, a standard candle, the definition of standard candle is it's basically an astronomical object that has a known luminosity. Okay, now the reason we like things with known luminosities is because we talked about this before. Because of the equation, B equals L over 4 pi d squared, we can directly measure B, that's the apparent brightness. If we can find some way to measure L, okay, the luminosity, then we can find D, the distance to that star. And distance to star is something we're very interested in finding. We can use things like stellar parallax, but remember that only works for relatively close stars that are close to us, within a couple hundred parsecs. Okay, and so we really like these standard candles, and a Cepheid variable is one example of a standard candle where we can very easily measure the luminosity of that object. Okay, so I'm going to go down here, and basically the relationship looks something like this. Okay, it turns out it's actually a linear relationship. Well, actually, this is not really a linear relationship because the y-axis is logarithmic scale. But basically, by measuring the period, we can measure the relative luminosity of a star and then use that to find the distance to a star. Okay, so let's see, going on, standard candle, we talked about this before. It says Cepheid variables with longer brightness periods are more luminous. With this table that's been made again over many years of observations, a lot of people took painstaking measurements decades ago to figure out this type of relationship. By just observing one single star and noticing how its luminosity changes over days or weeks, we can use this chart that's been created over many decades to figure out the relative luminosity. Okay, and so what we can see is basically the longer the period, the more the relative luminosity is. So we would just look at a star, measure at what time is it at its peak brightness, and then wait until it's at its peak brightness again, and that time in between is the period. Okay, and then we can use this equation that we talked about before to find the distance to that star. Now, the nice thing about using Cepheid variables to find distance rather than stellar parallax is Cepheid variables, we can use those even if the star is not in our galaxy. Even if it's like millions of parsecs away, we can still use this method to find the distance to that star. Okay, and so of course the downside is if we want to know how far away a galaxy is, there just happens to have to be a Cepheid variable in that galaxy, and we can't make there be a Cepheid variable in that galaxy, and so we're kind of limited by where do we find Cepheid variables in the universe? And if that galaxy happens to have one, then good for us. Otherwise, we have to do something else. Okay, but Cepheid variables or any standard candle method is really useful for finding the distance to a star if we can't use just simple stellar parallax. Okay, but again, this can be used up to a couple million parsecs. So here's just a simple example. Let's say we look at a Cepheid variable and we measure that the period of brightness to brightness is 5.4 days. Okay, and we want to know how far away is that star based off of that period of 5.4 days. Well, we would go to a graph or a chart that looks like this. Okay, we would find 5.4, and then doing our best to make an estimation, we would find the relative luminosity. Okay, so for example, on this graph, 5.4 days roughly corresponds, of course we have to make really rough estimates here, roughly corresponds to about 1500 of a relative luminosity. In other words, 15 times more luminous than our sun. Okay, and so we know that the luminosity of the star is 1500 times that of our sun. We know the luminosity of our sun, okay, because that's something that's known, and so we can easily find the luminosity of the star here, and then given that luminosity, we can plug back into the apparent brightness equation and find D. Remember, apparent brightness can be directly measured, right? You just point a telescope at something, you measure the amount of watts hitting your telescope, you divide by the area of the telescope, and boom, you've got apparent brightness. So apparent brightness can be directly measured. Luminosity cannot. Okay, so that's why this method is useful. Okay, so that's an example of what a simple calculation with the Cepheid variable would look like. Okay, so these problems tend to be relatively simple. Usually you're using either like a graph or a data table or something to find the relative luminosity, and then based off the relative luminosity to find the distance. Okay, and so I'm just going to do, let's see if I want to do one more example. I'll just do part of this problem really quickly. So it says the Cepheid variable is observed to have a luminosity period of about 3.5 days. Use the graph to the right to determine. So the first question wants us to find the luminosity of the star relative to our sun. So a period of 3.5 days, if we go up like this, would correspond to roughly a relative luminosity of 10. So this star would have a luminosity of about 10 times that of our sun. Okay, now the next question says the mass of the star relative to our sun. So you might think, well, wait, if we know the relative luminosity, how do we find the mass? Well, that is the mass-luminosity relationship that we talked about a few minutes ago. Okay, so remember the luminosity is proportional to the mass raised to the 3.5 power. Just to save space, I'm not going to write out the whole work over here, but you can set up the ratio just like before, and solve for this ratio. But basically, what you should get is you should end up with 10 to the power 1 over 3.5. And that should be, just type that into my calculator. Okay, that should be about 1.93. Okay, so the mass of the star relative to our sun is about 1.93 times the mass of our sun. Okay, now keeping in mind that we already have all this information just based off of looking at a star and noticing, the time between when it gets brighter and when it gets dimmer. Okay, that's an incredible amount of information to find just based off of that very, very simple observation that we can make. Okay, so I'm not going to do the last one just to save on time. The distance to the star in light years, you can easily use the apparent brightness equation to find that, and so I'm not going to do that for you. Only just to point out that remember in this equation for apparent brightness, D should be measured in meters, and so if it wants the distance in light years, you would have to convert that to light years. Okay, so convert. So again, to save on time, I'm not going to do that, but that basically takes us through the mass-luminosity relationship and Cepheid variables. And then the next part of this unit has to do with the evolution of stars, which I think is pretty interesting in its own right. Please let me know if you have any questions, and I will see you in the next video.